Now we're going to look at normal and tangential components. So if we have a particle that's moving along a curved path, the motion of the particle itself doesn't depend on the components that we use. So let's say we have a particle here, it's moving along a curved path. We can represent the same motion using xy coordinates, normal tangential coordinates, or polar coordinates. It doesn't change the motion of the particle itself, it's just moving along this path, but it does change the type of information that we get from our analysis. So for normal and tangential components, I'm going to show you where we're headed. So the acceleration of the particle will be equal to at, the unit vector is et, plus an en. The same equation written differently is a is equal to dv over dt, and in this case it's not the vector, so this is the change in speed with respect to time in the tangential direction, plus the speed squared divided by rho, which is the radius of curvature in the normal direction. So what this is saying is that this component of the acceleration is the rate change of the speed. So is the car going from 20 kilometers an hour to 40 kilometers an hour, for example? This term captures that part of the acceleration. This term captures the time rate of change of the direction of the velocity vector. The best way to think about this is, let's say you're driving in a car and you have a certain velocity, your velocity is equal to 20 kilometers an hour or something, and the radius of curvature of the turn is really wide. So this would mean that the radius of curvature, rho, is large. In this case, the normal component of your acceleration will be 20 divided by a large number, which means you have small normal acceleration. So you don't really feel that pull towards the center of curvature. But let's say you have the same velocity as equal to 20, and you have a narrow turn. So now your turn is really narrow. This means that your radius of curvature is really small. So then you have the same speed, 20, divided by a small number, going to be equal to a large normal acceleration. So this is why when you take a tight turn, you feel that acceleration so much more. And so when you analyze the motion of the particle in normal and tangential components, it means that you're capturing the rate change of speed and the rate change of that curvature, which is something that we weren't able to capture when we were analyzing our motion in the xy components. So when you're deciding which coordinate system to use, it's really important to consider the information that you're given and the information that you need to get out of the problem. So pretty much guaranteed, if the problem tells you what the radius of curvature is, that they're looking for you to solve the problem in normal and tangential components. So I'm just going to write down a few specifics about this coordinate system. Normal and tangential components are frequently the most direct and natural description for curvilinear motion. It's often used when the path of the particle is known. The normal and tangential coordinates move along the path with the particle. So this point here is the one that's the most different from x and y coordinates. And the positive direction for n at any point is always taken towards the center of curvature of the path. So let's say we're given a path of motion. So our path of motion, we're just going to define here arbitrarily. It's a curvilinear path of motion. The distance s will be the distance along the path the particle has traveled. So let's put our particle right here at a distance s. Now, the normal direction is the coordinate axis normal to the path. So that means that the normal is going towards the center of curvature from where that particle is. So if our particle is over here, our normal direction is pointing inwards here. If our particle is over here, it means that our normal direction is pointing towards the center. The unit vector for that will be En, and it moves along n. So I'm just going to draw En would be going along here, En is going along here. So the main point here is that the origin for the coordinate system is not fixed. There is no t is the coordinate axis tangent to the path of the particle. So in this case, your t starts at the particle and is tangent to the path of motion. It's always positive in the direction of increasing x. So this would be the t. Over here, this would be a t value tangent to the path of motion. Your et, which is your unit vector, is just the unit vector along the tangent line at that point. So I wrote out those definitions there as a reference point. Now, since the velocity of the particle is tangent to the path, we can express it as the product of the scalar v and the unit vector et. So we would have the velocity is equal to v et. Now the scalar of v is the speed, and the speed is equal to the derivative of the path of motion with respect to time, so ds over dt in the direction tangent to the path of motion. To solve for the acceleration equation, that's just the derivative of the velocity with respect to time. So acceleration is equal to dv over dt. If we expand this, this is d over dt of the speed times et. So we have to use the product rule. So we have dv over dt times the unit vector et plus the derivative of the unit vector with respect to time times the speed. In this case, this dv over dt is just the change in speed. So that's really straightforward. This is change in speed. And this et is just a unit vector, so we don't have to do anything. This is just giving us a direction. Here, we're just looking at the speed, so we don't have to do anything. But this piece here is a bit of a problem, because when we looked at the xy components, the unit vectors weren't changing because we had a fixed coordinate system. But now our coordinate system is changing as our particle moves, and so the unit vector is actually changing with time. So in order to explain what's actually happening with that unit vector, I'm going to do a small tangent. So I'm just going to move this up. And just a quick review. Let's say you have a circle here with radius of rho, and you want to find out a certain arc length. So let's say you want to know what the value of the arc length from here to here would be, and let's call that s. And we know that the corresponding angle between the 2 points would be theta. So the equation for this is s is equal to rho theta. If we take the derivative of this whole equation with respect to time, we end up with the derivative of that arc length with respect to time is equal to rho, because rho is just a constant, times the change of the angle with respect to time. We know that the change in path with respect to time is equal to the speed, so then we can say the speed is equal to rho times theta dot, or the change of the angle with respect to time. So we'll just keep that to the side, and now I'll explain what's happening to our unit vector En. So let's say we have here a path of motion like that, we have a center of curvature way over here. And we'll take the first point of our particle will be here. And so it has, the first point of our particle will be here, the second point will be here. So we have a unit vector pointing towards the center. Here's En. And then as it's moved, the unit vector has moved to still point towards the center, but now it's a different direction, En prime. We also have our ET vectors, tangent here, ET, and ET prime. So we're looking for how ET changes with time. So if we redraw just the ET vectors, the unit vectors, and we put them tail to tip, so our ET vector is in this direction. This is our ET. And our ET prime is here. Now our DET will be the vector that connects them. So this would be our DET. If we write this out as an equation, we have the new unit vector, ET prime, is equal to the first unit vector plus the change in the unit vector, and that's just simple vector addition. Now the magnitude of DET is equal to 1 times d theta. So if this is theta, we have DET has a magnitude of 1 times d theta. How do I know that? Well, this comes from what we derived a second ago, S is equal to r theta. And it is in the direction of En. I'm going to move this up just a little bit. So now we can say, I'm going to move over here, we have DET with respect to time is equal to d theta over dt in the En direction. Now if we look at this equation here that we derived before and we rearrange it, we have theta dot is equal to V over rho. If we plug that into here, we end up with, this is equal to theta dot En, which is equal to the speed over rho En. So I'm going to move this up and put all of these equations together. So now we have acceleration is equal to dv over dt, which is equal to rate change of speed in the tangential direction plus the speed times the change of the unit vector of the tangential unit vector. This is equal to dv over dt plus v times v over rho En. And this is the part that we just derived. Sometimes this equation is written out in a different form, so it's written out as acceleration is equal to at et plus an En, where an equals v squared over rho, and at is equal to the change in speed with respect to time, which is equal to v dv over ds, which could also be represented that way. Now the magnitude of the acceleration is equal to the tangential component squared plus the normal component squared square root.